Alright, welcome to another video on vibrations and waves, and we're going to be talking about a simple harmonic oscillator or a simple harmonic motion on a body. So in this example, what we have here is some sort of mass that is attached to a set of wheels, and it is free to roll on the surface. There's no friction, there's no slipping, there's nothing like that, and there's no air resistance. So this is a very idealized system, and it is attached to a spring of stiffness K. Now, the first thing when it comes to deriving equations of motion for any system is to draw a free body diagram. So from elementary physics, you will know that a free body diagram just accounts for all the forces acting on the system. So in this case, the spring is going to exert a force that opposes the displacement. So if the displacement is to the right, then the spring force is going to try to restore it back to its original equilibrium position. So it exerts a force in this direction. And that force is proportional to K times X, which is basically comes from Hooke's law. The next force is going to be the inertial force of the system itself, because it is going to be in motion. It is going to have some sort of inertial force, which is the net force on the system. And this is equal to the mass times the acceleration of the body. Now in this case, we're going to assume that there's no displacement, there's no motion along the vertical axis, so all the forces along the vertical direction are balanced, so there's only motion along the x. Now, according to Newton's laws, we can say that the sum of the forces in the x direction are going to be equal to the inertial force, or the net force on the body, which is just mass times acceleration, and this is going to be equal to whatever forces are acting externally. In this case, it is negative because it is going to the left. The next thing is we can write this equation in the form mx double dot equals to, plus kx equals to 0. So immediately we notice that this is a second order homogeneous linear differential equation with constant coefficients. Now we can solve it by first saying, okay, let's rearrange this such that we have k over mx equals 0. And now, since these are just two constants, we're going to replace this term by something called the natural frequency of the system, or essentially just omega naught squared. So we're going to see what this is about in a few videos later, but for now we're going to focus on how to solve this system. Now, first thing we're going to do is we can rewrite the equation as x double dot plus omega naught squared times x equals 0. And we know that we can find a characteristic equation by using a set of roots r and replacing the derivatives by power. So this is going to become r squared plus omega naught squared equals to 0. Now the next thing is, of course, we want to find the roots of this equation. And you know, since we have a positive here, this means we can factorize this by using complex numbers. So we can write I omega naught times r minus I omega naught equals to 0. So the roots of this equation are going to be plus or minus I omega naught. Now we know from the general theory of differential equations that whenever we have complex roots on our homogeneous second order differential equation, that corresponds to a solution of the type e times the real part of this, which is just 0. So in this case we just have the cosine and the sine terms, so a times cosine of omega naught t plus b of sine of omega naught t. So we can either write it in this form, or we can write it in the form using complex exponentials, which would be a times e to the I omega naught t plus b e to the minus I omega naught t. So these two expressions are equivalent if we let a and b be complex themselves. However, for simplicity, we're going to use this form because we can usually visualize what this looks like, whereas this complex exponential can get quite messy. So we're going to just deal with this thing over here. Now the next step is, of course, we will need some sort of initial condition. So we would need to know what's the initial displacement of this body in order to solve for the constants a and b. So in this case, we don't really need that because we already know what the solution is going to be. But we could say something like, okay, so let's say that at time equals 0, we have some constant displacement x naught. So that means that we're going to have a cosine of 0 plus b sine of 0. So this is going to be 0, this is going to be 1. Therefore, the amplitude of this system is going to be x naught. which means that we can write the solution to this equation as simply x naught cosine of omega naught t. Now let's look at this equation for a little while. So this is a simple harmonic motion, clearly, because this is what we discussed in the previous video. And we notice, okay, so we have an amplitude that is equal to the initial displacement of the system. So if the displacement is 30 centimeters, then this is going to be 30 centimeters. This is going to be the natural frequency of oscillation of the system, or essentially it's going to tell us the period of the oscillation, because we know we can relate the two by saying 2 pi omega naught. So there's this relationship between the period and the natural frequency of the system. And this is essentially what it's going to be. So if we were to plot this on a set of axes, what we would get is along the time axis over here, we're going to have the displacement along the x direction, and that's going to start off at x naught. It is going to go down, and then it's going to result back, and then down, and then back, and so on. So this is going to continue. This is not a good plot of a cosine function, but you get the idea. So this is essentially what we have here so far. So we have the amplitude, and now this is going to determine the period. So the period here, whoops, should be at the peak here, t equals 2 pi on omega naught. So that's essentially what we're going to have. So the first thing we're going to notice about this system is that there's no energy loss. And in order to do that, we actually need to look at the energy plot or the energy diagram corresponding to this system. And this is what we're going to do in the next video.